Good afternoon. So let's start lecture. Okay, so in previous lecture we started on double integral. Okay, so double integral basically, in essence, is you integrate a function of two variables over a region R. So, if graphically speaking, basically you have a region R given in the xy plane, and then you have a certain surface given on top of this region R. Okay, then integration basically means you integrate this function over the given region R here. So that's what mathematically what this basically means. We approach this formula using the concept of a volume. So basically, what's the volume below the surface and above the region R, right? Okay, but you can certainly use this expression for many other applications, as we're going to learn next lecture in terms of application of a double integral. So this function here could be a density function. So if this is a density function for the thin plate region R here, then it'll give us a mass, basically quantity, right? So it really depends on how we use it, and we're going to have different meanings. I illustrated how you basically evaluate this double integral. Okay, the process is basically to scan through the region R, and you can draw the region R in the plane, basically in the planar case. So you can always do different orders, dy, dx, or dx, dy. Okay, depends on the order, and then you basically will start to scan through this region R, or which what we typically basically integrate through this region R, right? For example, if I use dy dx, for example, then the first step you do is you will draw the arrow lines in the y-axis direction, and then you will move this arrow line right across this region R to find the edge. So first contact here give you y min, second contact give you y max. Then as you scan through the region R, then you get x min, and then you get x max. So this is how you basically find the limits for the integrals. Okay? Yeah. At the end of the previous lecture, and I give you an example to integrate basically the region R, which is a quarter of the circle here, and it turned out to be very challenging to evaluate, which is probably not a good idea to compute that way. So this is basically what brings to today's lecture. If one set of coordinates doesn't work very well, and we can actually have an alternative basically approach to evaluate double integral. So basically what this one here is doing is, this is called Cartesian, right? This is a Cartesian coordinates. Okay, it's x, y at here in xy plane. Okay. If that doesn't work very well, if it's turned out to be very difficult integrals here, so we can have alternative solution, which is basically use a different coordinate system, and this is a very common one. It's called polar coordinates. Okay, so let's look at polar coordinates and also the evaluation of a double integral in polar coordinates. Okay, and then we'll look at what's the advantage of this polar coordinate system here. Okay, yeah. Okay, so what is polar coordinates first of all? Okay, so let me move this down a little bit more here. Okay. Now, if we draw Okay, so if I draw a xy coordinate system here and pick a point in the xy coordinates, and this is basically with the coordinates of x and y, right? Okay, so now if I connect the origin with this point here and now define two new coordinates. One is theta, the other is r, which represent basically, it's like the complex number here, right? You know, you have an argument, you have a magnitude here. Oh, it's like a vector, okay? Yeah. Now this r and theta basically is the polar coordinates here. So r theta is what we call the polar coordinates. Okay. So this x, y here represent Cartesian coordinate system. And for polar coordinates, you can literally see how does theta move. Theta always moves basically around this center axis, right? And r always goes out in the radial direction. So that's what the direction of r here. So if I create a coordinate system, basically I can create a coordinate system this pointing to the direction of the r, the change of r. So let's say I use er hat. So this is I hat, this is j hat, the two unit vectors representing this two coordinate system, and we can create another unit vector in the r direction, another vector in the theta direction. So theta is always the moving of the theta, right? Is always perpendicular to this r here. So let's say call the e theta hat here. So this coordinate system is basically the polar coordinate system. Okay, yeah. So that's a new system. The difference basically, you see, the x and y coordinate system is fixed, right? Even if you pick a different point here, the x, y is still here. But if you pick a different point, the polar coordinates in this case here, we actually will have a time varying property at here, right? Yeah. So that's the difference. But you can easily create a connection between the polar r and theta and the Cartesian coordinates x and y at here. So if this is x and this is y, so apparently your x equal to r times cosine theta, your y equal to r times sine theta. Okay, so that's the connection between basically the polar and the Cartesian coordinates at here. So your x basically you can call it x is a function of r theta, and y is function of r theta 2. So we actually will illustrate a little bit more here next step when we have a general coordinate change. Okay, so this is basically a specific coordinate from Cartesian to polar, right? You use this relationship. Okay, polar coordinates is a very useful one. Some graph can easily be sketched using polar instead of using Cartesian. So for example, here we have two expressions in terms of polar coordinates r and theta, and they look very similar. The first one is 0.5 sine theta, this one is 0.5 sine 3 theta, and the drawing come out basically is like a cardio type of drawing here. Depends on the coefficient for the theta. Okay, as you have 3, then you have 3 basically petals that are here. Okay, imagine you have more, then there will be more, right? Yeah. So that it's another branch of basically mathematics here in terms of how you can sketch out things using polar coordinates, right? Okay. Okay. So the point here is we wanted to basically evaluate a double integral using polar coordinates instead of Cartesian coordinates. Okay, so let me rewrite the double integral here. Okay, so here is a double integral, right? Yeah, here's double integral here. Okay, so now the point here is I'm not going to deal with x and y anymore. Okay, so basically, remember that at this stage, I want to actually use r and theta instead of x and y, right? So that's what we're going to do. So basically, the way you can think of it is basically, okay, so for this particular double integral, okay, so I'm not gonna use x and y, right? So what do we do with x? I'll just replace the x with r times cosine theta, and the y replaced with r sine theta. Okay, right? That's the f function. The x, y will disappear, and instead the r and theta will come into the picture now. Right? Now the question here is, what do we do with this dA at here? Right? So this dA at here, basically this is a area differential. It's a very small area, infinitesimal small area. In Cartesian coordinates, this can be equal to dx dy or dy dx, right? So basically, it's the quantity small change in the x direction times quantity change in the y direction. You get a small area, a rectangular area dx times dy, right? Okay. So the problem here is, if I change from xy to polar, then naturally, instead of dealing with dx dy, so we're probably gonna deal with dr d theta, right? Dr d theta here. Okay. Yeah. But the question here is, shall we just directly change the dA from dx dy to dr d theta, or should there be something at here, right, to make some changes? Okay, so that's basically what we need to figure out right now. Okay, so what should be this thing at here? Okay, yeah. Okay, so I'll show you actually two different ways. Once we learn the Jacobian transformation, then we can show you another way. But for now, let me use a similar approach, okay, for approximating a small area. Okay, yeah. So you see, in Cartesian, okay, here is how you would probably approximate a small area here. So this is what I mean here. This is dx, okay, and this is dy, right? So this dA equal to dx dy. Okay, so that's how you approximate the area in the Cartesian. So in polar, right? Let's try similar things in polar coordinate system. Because see, in Cartesian coordinate system, how do we draw this rectangle? Basically, we create two, right, vertical lines and horizontal lines, right? We create vertical line, horizontal. The vertical lines, the horizontal lines are both in the direction given by what? Given by the xy coordinate, xy axis direction, right? Okay. So in polar, let's try the same thing. Okay. Here's the polar. I'll still draw the xy here because it's just a comparison here. So polar, if you look at this drawing here, the polar axis direction is not in the xy axis direction. It's in this ER and then E theta direction, right? So that's the two things. Basically, ER is in the radial direction, and E theta is some sort of a rotating around this vertical axis direction. Okay, so this is what we do here. So let's say I'm gonna basically try to draw a number of radial lines, okay, which is in the ER hat direction. At the same time, okay, we'll draw a number of basically circles, okay, around this center. So now you see the area, right? You can separate the area now. You can have a small patch of area, which is indicated, can be, let's say, illustrated by this red one in here, right? So let's say if I explode this a little bit bigger here, okay? If I explode this a little bit bigger, okay? Okay. So suppose this is the one that we're looking at. So now I'm going to label something, okay, just like a dx dy, so I'm going to label something in here. Okay, so the first radial line here has a theta value. The next one here, there's a small change, delta theta. Okay, so next one is a small change, delta theta. And this is basically, consider this is a circle here, okay? This is a circle. And this circle has a radius of r. So this is all circles, so this is r, this is r, this is r, okay? Yeah. And then you have a change of the radius from here to here, a delta r change. So the x, or dx dy, so now here we have a delta theta delta r. Okay, yeah. Okay, so now I'm gonna focus on the differential area at here. Okay, so the area differential for this small region. Okay, now this is a very small region. If you section your region using a very closely clustered radial lines and also this circles that are here, even though those are curves, but because they're so small, you can still consider this region as if it's a rectangular region, okay, or parallelogram basically. Okay, yeah. So bottom line is, then you would be able to obtain the area using a rectangle formula, right? Okay. So if I use a rectangle formula, basically the area will be what? This side multiplied by this side here, right? Okay. Rectangle, basically you consider this is same thing, this and this is same thing, okay? Because it's a very small change, right? Yeah. Okay, so this side is very easy. This side is just delta r, isn't it, right? So it's delta r. So what about this side here? Okay. Okay, what about this side or this side? Same thing. Okay, consider it's a small. So this is an arc, right? Technically speaking, this is an arc, and the arc has covers an angle, range of angle is a delta theta, with a range of with a radius of r here. So this little arc length here should be what? R times delta theta, right? So r radius times angle give you the arc length. So bottom line, now you see the rectangular, you consider this as a rectangle, then the area of this rectangle is what? One side times the other side. So now you have your delta A at here is approximately equal to delta r times delta theta. Okay, so that's how you approximate this little area, right, in the polar coordinates using polar, because this is how we section this, how we create this one here. We created this one as using the polar coordinate system. Okay. So let's rewrite this one here as r times delta theta. Good. And you can imagine if your sectioning process using an infinite smaller sectioning, so the delta will become straight d, and this delta also becomes straight d, this delta also becomes straight d. So that basically the differential area in the polar coordinates is dA equal to r times dr times theta. Right? That's it. So go back to the formula here, right? So this is exactly what we're looking for. So I'm not trying to evaluate using x, y. I'm trying to evaluate using r and theta. If I change x and y to r and theta, the dA, instead of this dr d theta, so this question mark at here this should be r at here. Okay, so there should be r, okay, like this. So this is basically the connection, transitioning this double integral from Cartesian to polar coordinates. Okay, yeah. So let me rewrite this double integral here because we're going to use it. Okay. So that basically equal to so this is what happens in here, right? Yeah. Okay, so now we've got the formula, but this is not the complete picture of the formula yet, because you have everything in terms of r and theta now. But the question is, we wanted to evaluate, we wanted to compute, we want to obtain a value out of double integral. So we have to, like this one here, you need to figure out the limits for x and y. Then here, you need to figure out the limits for r and theta, right, in order to evaluate this double integral here. Okay, so the next step here is we want to evaluate this double integral, or try to find the limits for r and theta. let's see how we can evaluate this when using polar coordinates. Okay, yeah. To find the limits, okay, or to evaluate this double integral using polar coordinates, the focus is still on the scanning through this region R here. Okay, yeah. So I'm going to use an example here, and then also to illustrate the steps that here to evaluate this double integral here. Okay, step 1. Okay, sketch region R. Okay, and label the boundaries. Okay, so I'll use a sample region to illustrate the process. Let's say suppose that this is my region R. Okay. So this region R here are bounded by 3 curves. One is the y-axis. The other one is a portion of this circle, x squared plus y squared equal to 4. So the radius of the circle is 2. And then there's also a segment of straight line here. So that's y equal to root 2. Okay, so that's 3 boundaries at here for this region R. Okay. Okay, so now step number 2. Okay, so we're trying to find the limits now. So let's see, in this here, we're trying to find this R limits. Okay, for integration. So R limits for integration here. And this is what you do. Okay, starting from origin. Okay, start from origin at here. You draw a reading lines out of the origin, okay, across this region R. Okay, so that's basically the first step here. So draw a reading line, okay, from origin. Okay, through region R. That's what happens here. If you recall that for finding the limits for the Cartesian coordinates, what do? We draw arrow lines in the direction of either the x-axis or the y-axis, isn't it, right? So here we draw the reading line, or in other words, I actually draw an arrow line in which direction in the polar coordinates r-axis direction, right? Yeah, so it's the same idea. Then your first contact, which is the entry point, will give you r mean, and your second contact, the exit point, will give you the r max. Okay, so first contact give you r mean, and second contact will give you this r max. Okay, so the limits, the minimum and the maximum for the integration, the limits. Okay. So let's take a look at what does it mean by r mean and r max, right? So first contact is here. Okay, this is here. So for this particular location, basically, what is the value of r, right? That give us this r mean. So if you look at this location here, so basically this portion, right, is this r mean. Okay. Second contact is at this location. So you can try to find this length at here. So that length will give you this r max. Okay. So that's what we mean by r mean, r max. Okay, it has to be referencing to the polar coordinate system. Okay, So R mean, R max. So let's take a look at this. Is sometimes what really would trouble some students here. How do you find this kind of R mean and R max here? Because why? Because you look at let's look at the easy one here. Let's look at the easy one. What's R max? What is the value of R max? 2, right? Yeah. So really, it doesn't matter how you draw this. You draw it here, you draw it there. The second contact is always on the circle, right? Which basically the R max is the radius of the circle. So that's good. So this R max always 2. Okay. But R mean is a bit tricky because you draw here or here, so that R mean actually changes, right? So that's basically it's a time not a time. It's a varying quantity, depends on where you draw the line. But we do need an expression for the R mean in order to do that. In order to do this integral here. Okay. So let me basically redraw that here, just to illustrate the finding the R mean value here. Okay. Okay, so it's this portion and here we're looking for, right? It's this portion. Okay, this portion. So you're integrating with respect to R and theta now. Okay, so you have R and theta, 2 variables, and your first limits you're finding is R at here. Okay, then the R expression at here. Okay, in this case has to be a function of theta. Okay, so let's label something here, because you draw the arbitrary reading lines at here. So arbitrary basically means really doesn't matter I draw, it got to have a certain value of a theta associated with this reading lines, right? So that will be a theta here. Okay, yeah. So now it's a matter how you use your trigonometry and geometrical relationship to find the R mean now. So I want you to focus on this right triangle here. Okay, focus this right triangle. So let's draw the right triangle out at here. What's this height of this right triangle? This side. Good. It's a √2, right? Good. And this side here, I don't know, right? So because it really changes here. And this one here is your R mean. The hypotenuse here is R mean. If this is a theta, okay, if this is theta here, then what's this angle here? No, theta, right? Yeah, geometry. Okay. Okay, so now you got your right triangle. Can you find a relationship between the R mean and theta? Right, what will be the R mean and theta? Connecting the R mean and R theta together. So sine theta equal to √2 over what? R mean. So R mean equal to √2 over sine theta. Right. So that's your R mean. Right? And you know it's a varying quantity. Okay? It's not a constant. So this is apparently true, right? Depends on where you draw it, how much the theta is, then your R mean will take a value from here. Good. So that's basically your limits for the R mean at here, and you can write it using cosecant theta. Okay, that's fine. Okay. Usually I just keep it as sine theta. Okay. So once we find the theta limits, the R limits, then the next step will be the theta limits. Okay, the theta limits. Theta limits here, you need to go back to the original drawing at here. So this is the first we created a reading lines here, right? Yeah. So when we create the reading line, technically speaking, what we just created here is basically it's a segment of a line. So you essentially just scan through from here to here. Okay, it's a very, very, very thin line here. You created this line here, but you wanted to do what? You wanted to scan through the whole region R, isn't it? Right? Scan through the whole region R. So the next step here is you're gonna have to rotate this reading line. Okay, can you imagine what happens? Rotate it up to from one end, okay, to the other end. So you can imagine the rotating of the reading line here will go from here and end up over here, right? Okay, that's the sort of the edges for the region R. That make sense? Okay. So let me see if I can. So basically, you're doing this, right? So you're scanning starting from here. This is the beginning edge. Then you scan through this whole region R. Okay. As you're scanning through it, you can imagine that what created is you're basically recreating this region R here. Okay. So not just the one single black line, you're actually recreating this region R here. So your theta basically is associated with the two edges. One is this edge, so this will be the theta mean, and the other end here will be the theta max. Okay. So that's the idea for scanning through this region R, right? Yeah. So apparently you can see theta mean may not be so clear, but theta max equal to what value? Pi over 2. Okay. Yeah. So you need to also remember one thing. The theta angle, for this class, okay, or for every class probably, the theta angle is always respect to the horizontal x-axis, and you always take it as a positive when you count it in the counterclockwise direction. Okay, and you always go counterclockwise direction as a positive direction. Yeah. So that's something you got to remember here. Okay. Yeah. So apparently your theta max, okay, I'll write something here. Okay, so rotate reading line, okay, across region R. Okay. The two edges will give theta max and theta mean. So in this case, theta max is pi over 2, and the theta mean we'll try to figure out by a little bit of calculation here. Okay, yeah. So theta mean, we do know that it's the theta angle associated with this particular reading line, and that particular reading line basically is here. Okay, it's this one here. It passes through the intersection between the circle and this horizontal straight line. You can easily find the coordinates, okay, for this particular point is root 2. So your theta angle associated with this line must be pi over 2, right? Pi over 4. Okay, yeah. So you can, how do you solve it? Basically, you see here, this is a circle, x squared plus y squared equal to 4, right? The horizontal line here is y equal to root 2. So if you substitute y equal to root 2 into the circle, and you get x equal to root 2. Okay? Yeah. Does that make sense? Yeah, that's right. So this is your mean, theta mean, and this is your theta max. So finally, you can set it up now for this region R. So you substitute, of course, x with r cosine theta, y with r sine theta, and then you replace the dA with r dr d theta, and then r goes from, as we just figured out, r goes from root 2 cosecant theta to the radius of the circle, which is 2. And theta goes from pi over 4 to pi over 2. Okay. Yeah. So that's the process, finding the limits for the r, and then finding the limits for the theta. So 2 steps of scanning. One is scan in the direction of reading direction. The other is a scan in the circular direction. Okay? Yes. Oh, no. You're not trying to get the area of the region here. Okay? This is see here. This is integrating over the region R. Okay? So what you're doing here is, see this function here, right? You're integrating this function. This is some function. This question was not given, right? It's some kind of function. Integrate this function through the region R. So basically, how you're scanning through the region R here. So it's not like you're calculating the area of this region R. Okay. Yeah. So you might think, what you might think is, it probably works, is you can integrate the whole function, okay, basically using this pizza first, this section of region, and then minus this guy here. So that actually probably will work, right? But I think that's even probably more complicated. You might as well just integrate through this region R directly. Okay, yeah. So I'll show you an example. You'll see what this process really means here. Okay. Yeah. Yes. Okay. So you see here, what's that? To find the theta limit, you're gonna rotate these reading lines, right, from one end to the other end. Okay. So this end is basically just pi over 2, right? And this end is the line passing through these corner points, right? Yeah. For the corner points, you see the horizontal line here is root 2. Basically, the coordinates for the horizontal lines, the y is always root 2. So you can substitute y over equal to root 2 into the circle equation. So 2 times 2 to the power root 2 to the power 2 is 2, right? And then you solve, you get x equal to root 2, right? So the coordinates for this corner point is root 2. So that theta angle corresponding to the line passing through the point is 45 degrees. Yeah. Is that good? Yes.
Last question. So for x squared plus y squared equals 4,
yeah.
When you say r squared equals 4, how do you know that r is 2 and not negative?
Very good point. The whole point of the polar coordinates defining the r, right? Make sure that r will be always a positive number. Because what is r? You see the r here? You see the r? R is defined as basically the distance from origin to the any point in the space, right? So that gives you basically it's always a positive number. Not in polar coordinates. Yeah. Yeah. Did you see r negative r somewhere in your example? Yeah, so you can't have negative links, right? Yeah. So r is always basically between 0 and something, okay, an infinite number or some other value. But theta could be negative, okay? Theta could be negative. So as you're going to see some examples. So let's say, for example, theta goes from here to here. In that particular example, theta is basically theta is pi over 4 to pi over 2, right? So that's positive. But sometimes theta goes from below the x-axis to above the x-axis. So in that case, you can actually have it from a negative angle to a positive angle. Okay? Yeah. Because remember, the definition of theta is always what? The angle between the line and x-axis, right? So if you draw a line from the bottom here, okay, let's say if this is one edge, so this angle here, you draw it here to here, so that'll become a negative theta now, okay, so negative angle. So that could be a negative number. Okay, so let's look at an example here, okay, to illustrate this here. So let's say I have a function f of x, y equal to this. And the region R is x squared plus y squared less than 1, x greater than 0, y greater than 0. So this is basically more or less the example that we couldn't finish, or are too hard to finish for the Cartesian double integral at the end of the previous lecture. So let me draw the R here, okay? Both x and y are greater than 0, and this is just basically the circle. So you're looking at just a quarter of the circle here, right? Okay. Okay. So if I wanted to illustrate a little better here, basically I can draw a 3D at here. You're looking at essentially a quarter of the circle, and that's your region R. Okay. And then on the top of the circle, you have a function f of x, y equal to 1 minus x squared minus y squared. That more or less it's like inverted, basically more or less like an inverted a bow like this with a maximum value of 1. Okay, so that's sitting on the top of this quarter circle here, right? Okay, yeah. So that's basically the double integral we're trying to find out at here. Okay, so that's a double integral. If you try Cartesian coordinates, you will find it's very hard to solve. So really what we wanted to re-evaluate this one using polar coordinates, right? Using polar. So using polar coordinates, we're going to have to deal with a couple of things here. So let's look at this function, okay, by substituting the x and y with polar coordinates. Remember what you do with x, huh? X, you replace x with r times cosine theta, and that it's x squared at here. Then you're going to replace the y with r sine theta. Good. That actually reminds me the line integral kind of question in the midterm. So when you do integration, the function, in that case you replace the x, y, z with x of t, y of t, z of t. Some student really confused there, right? Yeah, just find the right place and do the right replacement. Okay, so let's look at this one here. You can do some simplification. So this is 1 minus r squared cosine theta squared. This is r squared sine theta squared. So there's a common factor r squared. When you factor it out, you got a cosine theta squared plus sine theta squared, which is 1. So altogether you get 1 minus r squared. So this function f will be 1 minus r squared. Okay? Yeah. So now I'm gonna write down the setup of this double integral right here. Okay? So that's basically the set it up, and the only missing piece is the integral limits. Okay? For the integral limits, I'll follow the process that I just illustrated at here, okay, to find the limits. So here is your quarter circle here. So what do? We're starting from our origin. We draw a reading line out of this, or use like this, right? Out of this region R. First contact R min, second contact R max. So what's R min in this case? Yes, and R max is 1. Okay, so that's an easy one. So there's no variations. It's all two constants. Then you're gonna rotate this reading line from one end to the other end, the sandwiching this region R. So in this case, one end is here and the other end is over here. So your corresponding theta value for the two reading lines are the theta mean and the theta max. So the bottom one is 0, and the top one is pi over 2, right? So that's pretty easy. Okay, so that's basically the limits for the theta at here. Okay, so now you got everything. Then you just have to do the integration now, right? And this definitely a much better looking integration than the integral when you're doing in the Cartesian coordinates. Okay, should be quite straightforward. Okay, so the inside here, don't forget you have R here. I don't think in time student forgot. Oh, there's R. So it's actually R times R cubed. So there's 1/2 R squared minus 1/4 R to the power 4, and it goes 0 to 1 and d theta. Okay, so you get 0 right here. This whole chunk turned out to be 1/4 d theta, and then the whole thing equal to pi over 8. So that's a much easier way of doing this, right? Much easier way of doing this. Okay. So polar coordinates. So what I can tell you is, the question here you probably will ask is, so when do I use the polar, when do I use the Cartesian coordinates, right? Yeah. Cartesian coordinates are like a jack of all trades. You can apply it to any type of question. But for polar, it's more specifically to region, like a circular type of region. Okay? Yeah. And especially it's a circular type of region centered around the origin. Okay? So that's when we'll better use the polar coordinates. Okay. So let's look at another example, okay? Before we move on here. So the region R here is a half donut here. Okay, basically sandwiched by two circles. Okay, so this is the region R and C. Okay, yeah, and now we're trying to evaluate this double integral. So y dA here. So I'm not going to evaluate using Cartesian, so I'm going to evaluate the whole thing using polar. So the y at here will be replaced with r sine theta. dA will replace with r dr d theta. Okay. And the next step is to figure out the limits for the double integral. To figure out the limits, you starting from origin, then you draw a reading line out of the origin at here. First contact give you R mean. Second contact give you the R max. First contact is on the inner circle. Second contact is always on the outer circle. So the R mean is A, R max is B. Then you will rotate that reading line, okay, to go from one edge to the other edge. So in this case, one here horizontal here, the other is the opposite way. So your theta goes from 0 to pi. Okay. Yeah. So finally, you can do the evaluation, and this is still quite easy evaluation in here. So you will end up with this number. Okay. So try this yourself. Okay. And you can also try to do this question using Cartesian. See how difficult that it is. Yes. Sorry. A to B, you mean?
No, just about where it's double integral of the region y.
Which one is
To the left side. Just about the pi.
You mean here?
integral of R.
Double integration.
Oh, this one? What?
Where you wrote.
Oh, this, why? Oh, there's no y. This is what it's asked us to do. Just integrate this function. This function here, this is your f of xy. F of xy equal to y, basically. Yeah.
Is that sorry, that's,
Yeah.
is that a 2 over 3?
2 over
Is it
3.
two?
Yep, 2 over 3, I think so.
Why
Yeah.
is it 2 over 3 squared?
You're gonna have to evaluate this because you got a r square here, right? When you integrate, you get a 1/3 r cubed. Yeah.
So where's the 2 coming from?
The 2 will come from the sine, I believe. So you see that's 0 to pi integration for sine theta.
Oh, this is the entire.
Yeah. So in of the negative cosine, right? From
Yeah.
0 and then you got a 2.
Oh no, I did get 2 on it.
Yeah. Very good.
I thought it was just the first difference.
Yeah. Okay. All right. So the only kind of a trick kind of question for double integral is what is this kind of question. Okay, is this is to give you a irregular type of circular type of region, and then you are required to find R mean, R max, but the R mean is not a constant, or R max is not a constant. Right, depends on how it looks like. Okay, I believe last year I tested such kind of thing in the final exam. Okay, so basically this is only type of trick, and you have to see clearly which part is R mean, and through what type of geometry you can figure out this R mean, right, or R max. You know, really depends on this region here. Okay, otherwise I think it's pretty straightforward, and of course there might be some type of things, some type of technique that you need for integration. This is very simple, right? Yeah, very simple integrals. Okay, so that's all about polar coordinates. Okay, any questions so far? Okay. So now next general question is, now you may ask is, okay, so you have a Cartesian not work, you do polar works. So what if a polar not even working, right? So what if actually you wanted to, is it possible, you know, we have other options instead of Cartesian, instead of the polar coordinates? Okay, yeah. So the answer is definitely yes. So this is basically the next type of question here. It's the general change of variables. Okay, general change of variables. So basically what it means is essentially, sometimes instead of saying change of variables, you could also say it's a change of coordinates. Okay, change of coordinates. So I'm going to rewrite this double integral here again. So this is your starting point, right? So integration of this function over the region R with respect to the x and y coordinates. Okay. So general change of variable basically means is, instead of using the x, y variable, you will use a different set of variable or different set of coordinates. So let's say in that polar coordinates, then what did you use? You used r theta, right? Okay, that's specifically polar coordinates. But in general, right, what I can write is, I'm not going to use x anymore. I'm going to use a new set of variables u and v. Okay, so your x and y will be expressed using new variables u and v. So I don't know what that connection is, but somehow we'll be able to figure out. You know, maybe x equal to u plus v, y equal to u minus v, or x equal to u plus 3v or something, right? So there's some sort of a connection, basically. Okay, if that's what we wanted to do, then how that double integral will transition into, right? So that's basically the idea. Okay? So the idea essentially, you can see, okay, so if I have this relationship, then your original double integral, your x will be replaced with this function, and here will also be replaced with u and a v for the y. Your dx dy, right? Instead of dx dy, you're going to have a du dv at here. The same question remains here. So what will be a scaling factor, right? Should that be just a simple 1 or should that be something else? What will be an expression at here representing this question mark? Okay, yeah, that's what we need to figure out for this question mark at here. Is that good? Yeah. Okay, to figure out the question mark, so let's back off a little bit. Okay, so we're gonna define, okay, a so-called coordinate transformation vector. We'll define a vector function. So the vector function we define here is actually quite simple. It's basically this x and a y. Okay, so we're just basically defining it into a vector function here. So the x of uv, y of uv, okay, put them together, okay, define it as a vector function. And this happens to be called coordinate transformation vector function. Okay. Yeah. Now once you have this vector function now, then we'll be able to construct ourselves the so-called Jacobian matrix. Okay? Yeah. And you learned Jacobian in numerical analysis, right? Yeah. Have you learned? Yeah. So what's a Jacobian matrix? Let's see, if I have this vector function here, what will be the Jacobian matrix? This is a 2 by 1, so the Jacobian matrix will be a 2 by 2, right? Yeah. So the first row, what will be that? Partial x over partial u, and then partial x over partial v. That's your first row. And the next row is partial y over partial u and partial y over partial v. Okay. Now this is called a Jacobian matrix. Very useful. Okay, very useful. As a matter of fact, basically it's the first derivative of a vector function. Okay, Jacobian. The next second order, you're going to end up with the, actually, I don't know if you remember, when we learned the minimum maximum, we have a matrix called Cartesian matrix. So that will be the second order there. Okay. So that's a Jacobian matrix you can easily derive based on the given relationship for x and y, okay, between the x and y and the u and the v. Once we get this one here, we can calculate the determinant of this Jacobian here, okay, the determinant of the 2 by 2. So apparently the determinant is just basically you add a vertical sign in here, so that's basically you calculate the determinant. Sometimes the notation wise people write it like this, okay, so this is basically representing the determinant of the Jacobian matrix. Okay, sometimes they call it Jacobian determinant. Okay, yeah. And then I will just write down the results at here, okay, without giving the proof. So now remember, I'm trying to look for the question mark at here, right? The question mark. So the question mark at here, basically for change of variable, right, here is your original double integral. Okay, and now for the new double integral, your x becomes x uv, y is replaced y uv, then you have a du dv at here, and this blank space at here is the absolute value of the determinant of that Jacobian matrix. Okay, so this one sign here, so whatever the determinant you calculated, put absolute value over here, and then that's it. So everything now on this side here, we're all in terms of the u and the v now. Okay, the u and the v. Okay. Now, in terms of the subscript here, this is not, because now we change from the xy coordinates to uv coordinates. So this actually involves a transformation. So originally you have a certain type of region R. When you transform to the uv coordinates, that region, that particular shape, okay, will actually become some other type of a shape. You know, originally maybe it's a rectangle, and then it'll become a sort of deformed whatever other shape. Okay, so this is basically what I call it R prime, because in a different coordinate system, the shape actually looks different. But for example, right, if I have a xy here, if I do a rotation, so originally it's this. Once you do a rotation, so that looks like this now, right? So it's different. Okay, yeah. So it'll be slightly different R prime. This is actually the whole idea of doing this change of variable here. Sometimes integrating over the R is very difficult because it's a very sophisticated shape form of region. But once you use the change of variable, you actually have a much better region R to the region here to deal with, right? Okay, so I'm not going to give you a very formal proof for this one here. Okay, the formal proof is actually by Leonardo Euler back in the 1800s. So it's a very sophisticated proof. Okay, honestly, there's 10 pages of paper you can find on the internet regarding the proof at here. So we're going to just use the results at here. Huh? Yeah. But I want to illustrate this idea here with a very simple example first. Okay. Yeah. Very simple example. Simple example basically means I'll use that. Okay, I'll use this the Cartesian and polar coordinates to illustrate the change of variable concept. So here's your x, here's your y. Okay, then the Jacobian at here is partial x over partial r, partial x, partial theta, partial y over partial r, partial y over partial theta. So let's calculate this thing here. Okay, partial x over partial r is cosine theta. Partial x over partial theta is negative r sine theta. Partial y over partial r is sine theta. Partial y over partial theta is r cosine theta. Okay, that's your Jacobian, right? That's the Jacobian. Then, if we calculate the determinant of the Jacobian, so that's this times this minus this times this. So you just basically you get r cosine theta plus r sine theta here square. So take out the common factor r, so you get just basically got an r here. R is always a positive number, then the absolute value of this determinant is still r, right? Still r. So now you see your originally dA is dx dy, and then in the polar it becomes r dr d theta, right? Dr d theta. Okay, and that's exactly the scale that r we find using that approximation approach, right? When you find the differential area, we use that approach. The same answer here, and this is defined using the Jacobian approach. Okay, change a variable here. Okay, yeah. So let's look at another example here. Okay, so application of the application of this. Okay, so I'm gonna give you a sort of a complicated I'll give you a parallelogram in here. It's like a diamond here. Okay, so this region R here this is a diamond in here. If it's bounded by 4 different curves, x plus y equal to 0, 2x minus y equal to 1, x plus y equal to negative 2, and then 2x minus y equal to 3. Good. Basically, mathematically, this one here, this r, can be written as negative 1 less than 2x minus 1, negative 3, negative 2 less than, okay, like this. So you can label the r, okay, using mathematical expression like this. there are 4 lines basically. On the top of the line, below the line, right? That's basically what gives you this region R. Alright, now we're trying to integrate this double integral. So your function here is f of x, y. Okay, it's just a 3x. Okay, so integrate this double integral here. Okay. Now to evaluate this double integral, okay, I'm actually gonna come up the properties right after this one here. So if you are going to evaluate this one here using Cartesian, using Cartesian coordinates, forget about the change variable first. Just think straight using Cartesian coordinates. There is a problem basically here is, let's say if I decided to do this dy dx as order, yeah. So if I try to do using dy dx, so what's the process doing finding the limits? We'll draw an arrow lines in the y direction, isn't it right? And then find the y min, y max based on the first, second contact. But see, the problem here is, if I draw it here, this is y min, this is y max, isn't it right? But if I draw it here, this is y min, this is y max, it's different, isn't it right? It's different, okay? Yeah. So for this question, which will touch that right away, basically, if you use a Cartesian, okay, you're actually gonna section this region into 2 parts, okay, into 2 parts or 2 regions. You integrate this region here first, then plus the integration of the other part of the region. So that's basically what we call piecewise integral. Okay, it's like a single variable function. You integrate from 1 to 2, then 2 to 3. Right, that's a piecewise integration. This is double integrals piecewise integration. Okay, yeah. And one of the assignments basically it's like that. Okay, yeah. Now, but I'm not going to try that. We'll try a different example on that. But for this example here, I'm going to actually use a change of variable approach, and you will see it's much simpler than the piecewise integration. Okay, yeah. So what type of basically change of variable we should use? This is what we're going to do. We're going to let u equal to 2x minus y. The v will equal to x plus y. Okay, so introducing 2 new variables, u and v. Okay, so this u and v are introduced at here. So you see, if I wanted to use the change of variable, okay, so use this change of variable here, what do I need? I need an expression for the x and y in terms of u and v, right? Okay, yeah. What's your question? So, oh, should that be negative 1? No, positive. Oh, sorry. This. What did I write here? Now this should be positive here. Yeah. Good. Yeah. Okay. And then, so if you define u and a v at here, so then what we do is, here's the u. Let's do this. Is 2x minus y equal to u, x plus y equal to v. We're gonna try to solve for x and y in terms of u and v at here. Okay, try to solve this in terms of u and v. So now you can solve this. So basically, if you use equation 1 plus equation 2, so 3x equal to u plus v, and you get x equal to 1/3 u plus v. If you use 2 times equation 2, then plus equation 1, minus equation 1, then you'll be able to solve for the variable y, which is 1/3 negative u plus 2v. So that is your x uv, and this is your y uv. Okay? So this is the connection between x and uv, and the y and the uv. Okay? Which one? From here to here? So let's say this is equation 1, this is equation 2, right? So if you use equation 1 plus 2, what do you get? 3x equal to u plus v. And that gives you x equal to this. Yeah. Okay. Or you can do is you can use 2 times 2. 2 times 2, 2x plus 2y, then minus equation 1. So you get a 3y, right? Equal to what? Equal to 2v minus u, right? Yeah. Yes.
So to choose your u and v, you just eliminated the difference between the equations on the diamond and make one equation.
Yeah. So I think I'll rephrase your question probably. So probably you should ask, why did you choose your u and v like this, maybe, right? Yeah. So why? Because you see here, let's see if I choose u as 2x minus y, then what is the range for the u now? U is between 1 and 3, right? What's the range for v? V is negative 2, 0. So you see, the whole point here is, if you go back here, your original, it's a region R, in this case it's a diamond, right? And once the change of variable, then it's a R prime, it's a different region, but that region is sketched in the UV coordinate system. That make sense? So now you think about it, if I choose U at here, V at here, can you sketch this region R prime in the UV coordinate system? What does it look like now? Yeah, it's rectangle, right? It's not a regular diamond anymore. It's a beautiful rectangle, horizontal, vertical, as straight as possible, right? Yeah. So then you don't have the problem what? To section it into different pieces. Then you integrate the pieces, So that's the point of this change of variable, from a little more sophisticated region into a relatively easy region to do. So the idea basically, if you see, can I choose a different u and a v? Yes, you can. Yes, actually, and then it also probably also works, but it just may not be as easy as the choice over here, essentially. Yeah. Okay. So that's what we got here. And then I can calculate the Jacobian. So the Jacobian is partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Okay, so x is this, y is this. Very simple partial derivative. So we have 1/3, 1/3, negative 1/3, 2/3. Then the determinant of this Jacobian is this times this minus this times this, which is what? 2 over 9 plus 1 over 9. So 3 over 9, so 1/3. Right? Okay? So that's your determinant. It's a naturally positive number. So your original double integral will be rewritten. The x, you replaced x with 1/3 u plus v, because that's what x is. Okay, that's what x here. And your dA will become du dv with 1/3 from this determinant over here. Okay. The limits, your u, so your u is here, u is 1 to 3. Your v is negative 2 to negative 2 to 0. So basically 1 to 3, negative 2 to 0 here, right? Yeah. And this is a one. It's a very easy integration here, right? There's no trick at all. Okay. So you end up with a 4. Okay. It's very simple. Okay. If you do integration by pieces, it will cost you actually more time efforts actually. Okay. Yeah. So yes.
When you make those new coordinates, like u and v, are they perpendicular to each other?
Very good question. So yes, they're if you consider as the coordinates, then they're supposed to be perpendicular to each other. Yes. Yeah. But if you just simply consider as a variables, then forget about perpendicular or not, basically. Yeah. But if they're coordinate system, yes, one horizontal is u and the other side is v. Okay? Yeah. So now Jacobian is actually not a new concept to you guys. Guess what? What would be the Jacobian in one dimension instead of a two dimension? Right? What would be the Jacobian in one dimension? So let me give you a simple example here. So you're required to integrate this function, right? Okay, but you decided to not to use this, and there's an integration technique which is called what? Substitution, right? So you decided to integrate this using a substitution. So basically, I'm going to substitute x with an expression in terms of the u. Then your dx, right, will be dx over du, okay, and then times du at here, right? So it's basically. So you see this guy here, this is basically the 1D Jacobian. Okay? That's basically your 1D Jacobian. That's the substitution, basically. Okay? Yeah. The coefficient there is your substitution. Okay? Yeah. So it's nothing new there, actually. Okay? Okay. So I have a few minutes just basically to help with this one of the assignment question in here. Okay? Yeah. I just want to touch upon this one loose end. So integration by pieces for double integral. This is the property, basically what I'm referring to it here. Okay. So let's say I have a region R, which is R plus R1 plus R2. Okay. Then your double integral has this property, so you can integrate, okay, by pieces first, okay, and then add them together. So that's integration by pieces for double integral here, right? This can be easily identified when do you use this basically property. So I'll give you a simple example actually. Okay, yeah. So let's see, I have a region bounded by 3 lines. This line here is x plus y equal to 2, y equal to 1/2 x, y equal to 2x. Okay, so that's your region R here, huh? Yeah. So this is your R. Okay. Then suppose we're going to integrate some kind of function over this region R. Now this is basically the idea of the integration by pieces, because suppose I'm going to integrate, let's say, dy dx. Okay? Yeah. Then we're going to draw an arrow lines in the positive y-axis direction. If I draw it here, my lower limit is this line, upper limit is this line. But if I draw it over here, my lower limit is still this line, but then the upper limit changes, right? Change it to this line here. So that's why we will have to separate this region R by drawing a vertical line set here to separate it into 2 regions, R1 and R2. So R1 and R2. To get the double integral for both first, and then add them together. Okay? Yeah. So for this kind of question, number 1 step, what you need to do is you might want to figure out the intersection coordinates first, okay? Because that's where the limits really, right, for R1 and R2. Finding the limits is quite simple. Just combine 2 line curves together, and then you get basically the limits, right? Okay. So let's say this is A point, if this is B point. So for A point, you're solving y equal to 2x and this one. And for the B point, you're solving y equal to half x and x plus y equal to 2. Okay. So once you solve this, okay, so I don't have time anymore, but you know what? I'll go finish this in the next lecture. I think it's quite simple example. Okay. Yeah. Any questions? Good.